Hi y'all, welcome back to my channel. In this video we'll go over eigenvalues and eigenvectors. We covered this section a couple of days ago, so this is part 2 in which we'll solve practice problems. If you like this video, give this video a thumbs up, subscribe to my channel, and don't forget to share it with your friends. Let's get started with the first problem. So the first problem is basically the same as this one. So we have the matrix three, 2, 3, 8. Let's find out if lambda equals 2 is an eigenvalue. So we know this equation. So we can take the determinant of this in order to get the eigenvalues for this matrix. So this would basically be determinant of 3 minus lambda, 2, 3, and 8 minus lambda. On a side note, I'll just mention how we did that. So we have the matrix A is basically 3, 2, 3, 8. So we have the lambda, and we have our identity matrix, which is 1, 0, 0, 1 in this case, which is a 2 by 2 matrix. So we'll have I hope this makes sense of how we're getting this matrix right here. And in order to solve for it, we'll be setting it equal to 0. Since we're basically looking for lambda in this case. Since they're asking us if lambda equals 2 is an eigenvalue. Okay. So I hope we all know how to find the determinant of a 2 by 2 matrix is basically, if this is the matrix, A times B minus C times D. Let's do that real quick. I'm sorry. This is basically the diagonals multiplying. So right here. Okay, so simple math. 3 times 8 is 24 minus 3 lambda minus 8 lambda plus lambda squared minus 6. So here we have lambda squared minus 11 lambda plus 18 equals 0. Let's solve for this one. So factor it out. I think I might have skipped this step. Let me write that down so that you guys know where this is coming from. So that is lambda squared minus 9 lambda minus 2 lambda plus 18 equals 0. So we factored the lambda and negative 2 from the top one, and we're left with lambda minus 2 times lambda minus 9 equals 0. So we can solve this. Tee it off. Lambda equals 2 and lambda equals 9. So we'll just say yes, lambda equals 2 is an eigenvalue. Let's go over another one like this. Okay, so good. Okay. So for this one, this is pretty simple. It's very similar to what we did in the previous video. I did go over a couple of examples while going through the notes, so you might want to watch that video before going through these examples. So in this case, we'll start with the equation ax equals lambda times the x vector. So here we have ax as the a vector is negative 3, 1 and negative 3, 8 times 1, 4 I hope everyone knows how to multiply this by now. This times this, and then go with this times this. So the green one would be at the bottom, and the pink one is going to be at the top. Okay, so negative 3 plus 4, and negative 3 plus 32, and we're getting 1 and 29. So as you can see, there's nothing that could be written as lambda times x to be equivalent to this. So we'll just say no. So there exists no lambda such that ax is equivalent to lambda x. Let's go over another one. So let's move on to a new page. Also, I've been having trouble figuring out how to like do some noise cancellation in my videos, since like the pencil that I'm using causes a lot of weird noises in the recording. Let me know if anyone knows how to figure that out. Okay. So is lambda equals 4 an eigenvalue for this matrix? If so, find one corresponding eigenvector. So let's get back to our equation. Let's find out if lambda equals 4 is an eigenvalue. So we can do that by a minus 4I determinant equals 0, right? So we have so let's just do a minus 4I first. So this is going to be a 3 by 3 identity matrix, since we have like 3 by 3 matrix right here. So 4, 0, 0. I hope you all know how to form these by now. These are quite straightforward. So three minus 4 is a 1. -1, and then 2. 3 minus 4 is a -1 again. 5 minus 4 is a 1. This is what we have right here. And let's get back to our equation. This one right here. So a minus 4I determinant equals 0. And this would be okay, so it's a 3 by 3 matrix and we're looking for a determinant. So in order to do that, you can pick any row or column to find the determinant. I'll be posting, I think I might have posted a video on determinants. If not, I would fall in the following week. But if you guys already have an idea of how to get the determinants, you know how having a 0 in a row is very convenient. So we'll just pick this row. Now first, let's go with, sorry about that. Let's go with the -1. So -1 times, this is the left leftover that we'll be putting here. Oh my God. So we do have a 0 as well. If we go through 0, we would like have 0 times the matrix, which is basically just 0, which is why we're not putting that in. We'll go with the -1 in the third column. So let's just pick a different color. Okay, so this right here, and this would be, sorry, I just messed this up. So every time you do that, you have to multiply it with a -1 raised to the power row plus column. So in this case, the row and column are, so this is in row 1 and column 1. This would be 1 plus 1. In this case, -1 is just the -1 that we have here, and then we're gonna have another -1 raised to the row plus column. So in this case, we're in the first row and third column, times the matrix that we have here is gonna go right here. So just like okay, and we're gonna set it equal to 0, like we were doing. So if it's, so we'll be getting -1 times -1 squared times the determinant of this matrix would be -1 times 1 minus 1 times 4 plus -1 times -1 to the 4th power times the determinant, which would be 2 times 4 minus -1 times -3 equals 0. So -1 times -1 squared, so -1 squared is basically just 1, and -1 to the 4th is also just 1. So this is going to be -1 times this whole thing, which is -1 times 1 is -1 minus 4 plus -1 times this entire thing. So just remember that these are separate, so make sure you don't confuse them, because they're gonna change the calculations if you do that. So 5 plus a -5, so basically 0 is equivalent to 0. So therefore lambda equals 4 is an eigenvalue. In this case, we just proved that. Now we're asked to find one corresponding eigenvector. So we'll be finding the null space. in order to find the null space, we'll just write the matrix like, so we know that we find the null space by doing a minus 4I times an x vector is equivalent to 0 vector. Let's just write it as an augmented matrix right here. So we have the matrix with this right here. Okay, never mind. I'll just copy it down. Let's make sure if that is it. Yep. Okay. So we'll put the 0 vector alongside, and we have our augmented matrix. Let's do a bunch of row operations. We can do 2r1 plus r2. We have our new row 2 over there. We can get rid of this right here by performing negative 3r1 plus r3. So we're getting we can reduce this matrix to 1, 0, 1, 0, divide row 1 by negative 1, divide row 2 by negative 1 would be 0, 1, 1, 0, divide row 3 by 4 would just give me 0, 1, 1, 0. So we can actually do that. We see how row 2 and row 3 are same, so this is basically row equivalent to, it's just on the side note, it's just row 2 minus row 3, we'll just replace row 3, and we'll get 0, 1, 1, 0, and this right here. So from this matrix we see that x1, it's in row echelon form, first thing. So now we can take the equations. So x1 plus x3 equals 0, just to mention that. This represents x1, x2, and x3. Since we have the x vector over here, so this is basically the a vector times, so the a vector looked a lot like this. And we see that there are 3 columns, so we have x1, x2, x3 equals the 0 vector, which is just a 0 vector. eigenvector. Hope this clarifies the whole situation. Sorry I missed that step. The second row represents x2 plus x3 equals 0. The third row has no pivot, so x3 is free. So we can say x1 equals negative x3, x2 equals negative x3, and x3 equals x3 since it is free. So null a minus 4I is equivalent to the set of x3 times negative 1, and 1. So this basically, you can see how x3 times negative 1 would give me negative x3 for x1. x3 times negative 1 again would give me negative x3 for x2. And x3 times the 1 would give me x3 for representing x3. This is what it is. Let me know if you guys have any questions about that. And here x3 is a real number. So the bases that were asked for this would be the basis and the eigenvector. So the basis is basically the set, and the eigenvector is just the vector itself. I hope this clarifies a lot of things. Let's just do another problem. Let me just show you this problem all over again. So this is what we did. Let me know in the comments if I missed anything. Let's do problem 4. So we have matrix A with lambda equals 3, and it's asking us to find the basis for the eigenspace corresponding to each listed eigenvalue. So in this case we only have one. Let's get started. So first step, find null space. With the lambda 3. So this is basically easier since they've given us the lambda, the eigenvalue. So null space, to find null space, we do times the x vector times the 0 vector. So a minus 3I would just be 4 minus 3. So let's not skip any steps. Let's do a minus 3I. Three times the identity matrix would just be 3, 0, 0. So 3 times 0, 0, 0. I hope this clarifies the thing, where we're getting this from. Since this right here is a 3 by 3 matrix, so we use this 3 by 3 matrix for the identity matrix. This is what determined what the size for the identity matrix would be. Okay. So over here we're getting this matrix right here, so this is basically equivalent to a minus 3i. Now let's go back to this equation. So this is the matrix A minus 3i times x. So the number of x's are basically determined by the number of columns that we have. So that would be x1, x2, and x3, which is equivalent to the 0 vector. This gives us the augmented matrix. Right here, let's just do some row operations. If you're having trouble with row operations, it's one of my first couple of videos that I posted that'll help you a lot with that, so make sure to watch that before going in with this. So R1 plus R2 would help us cancel out this -1 right here, since we want to get this into row echelon form. So we're getting the new row 2 is just 0. So let's get rid of the third one right here. Can do -2 R1 plus R3 so we're ending up with row 3 as all zeros as well. This was row equivalent to 1, 2, 3, 0, and the rest are just all zeros. Don't write it like that, like write it in rows, not like me. Okay, so the first row says x1 plus 2x2 plus 3x3 equals 0. And since there's no pivot in row 2 and row 3, so x2 and x3 are free variables. Make sure you write that. That's like something that people usually lose points for. So x1 equals -2x2 minus 3x3. From the equation that we have right here, we just solved it for x1 since that's the pivot position. And we have x2 equals x2, it's free, so x3 equals x3 as well. So the null space of A minus 3i is equal to the set of x2 times. Before moving on to that step, let's go back and let's write out the solution for x So x was the vector x1, x2, and x3. And then we'll write in parametric form so that it doesn't confuse anybody. So negative 2x2 minus 3x3. Then you have x2 and x3. Now we're going to write it in parametric form right here. Okay. So x2 times, we see negative 2, 1, and 0 since just x3 in the third row. So negative 2, 1, 0 plus x3 times negative 3, 0, 1. Make sure to write that x2 and x3 are an element of real numbers. Or they're just real numbers. So just write it that way. It'll get your point. So the basis for lambda equals 3 eigenspace is both of these, the set of both of these vectors, and you should be good for this question. I hope this wasn't that bad. Also, yeah, to like help you with simpler stuff that we did right here or anywhere else, you can watch my previous videos so nothing causes any confusion. I do have some more examples that I would like to go over. They're pretty simple, but I'll just go over one of them. So it says find the eigenvalues of the matrices given below. So we have the matrix, so we see how this is a triangular matrix. Let me show you. So this right here is our triangle. This is like the other triangle if you want to see it that way, but like, yeah. So this way we know that the diagonals are the eigenvalues. And you can check that just to make sure. Like, I don't think you'll have to, since that is the answer. So in this case, like lambda equals 7, negative 4, and 2. You don't have to check that, but still you can check that with the technique that we used above. Right. In the first question that we did, as well as this right here. So we found out if 4 was an eigenvalue of this matrix. So we did a minus 4i, took the determinant of that, and then made it equivalent to 0. And if it was equivalent to 0, then we said that lambda equals 4 is an eigenvalue. You could do the same process for this one, but you won't really have to do that since like the diagonals are eigenvalues. I mentioned the theorem in my last video, so you can check back with that. I'll show you another example. So we could even have a matrix like so let's get the triangle in this case. This is 1, And this is like the other one. It's like the 3 zeros together. This part right here just determines that it's a triangular matrix. There's values in the diagonals but not on the sides, so in this case lambda would be 0 to -1. Let's go over another one. So what if you have the vector as follows, and you're told to find the eigenvalues without calculation. In this case, like, you see how this is row equivalent to 1, 2, 3, and like the rest are zeros, since like they're the same, so you could just subtract them. These rows are the same, so you could just subtract them, have 1 as the pivot, and the rest are like the free variables. This is like what it's equivalent to. And since you know that it's equivalent to that, so like without any calculation, lambda is equal to 1, 1 or 0. Hopefully that covers all of this section. It basically covers everything for eigenvalues and eigenvectors. We'll be starting off the next section soon. Hope you guys like my video. Make sure to give this a thumbs up and subscribe to my channel. I'll get back to you with the next video. Thank you.